In previous videos, we have defined distributions of random variables, expectations, and variances of random variables. In practice, we often are concerned with more than one random variables. To give you a simple example, one that we have considered before, in this example, you're thinking about making a decision about a medical insurance, whether to buy the medical insurance for the next year or not. Then two random variables are relevant for your decision. One is your medical expenditure without the insurance, and the other is the medical expenditure with the insurance. Let's say the first variable is denoted by X, and the second variable is denoted by Y. And their values corresponding to the three states of the world, no illness, mild illness, and severe illness, are respectively 0, 500, and 50,000 for X, and 100, 600, 600 for Y. And PS gives the distribution of the state of the world. This table can give us information about the distribution of X and the distribution of Y. So we can figure out the PMF of each of these random variables. PMF for X is like this. X takes three values, 0, 500, and 50,000. And there are three probabilities, 0.8, 0.19, and 0.01. The PMF of Y can also be figured out from this table. Y can take two values, 100 and 600. The probability that Y takes these values are given by 0.8 and 0.2. So the distribution of each random variable is part of the information provided by this table that defines multiple random variables, but they don't provide all the information there is. It doesn't, for example, tell us whether Y increases with X or not. In fact, it does in this case. It doesn't tell us about the dependence between X and Y in general. So we need some concepts to describe the dependence among multiple random variables. Let's start with joint distribution, covariance, and correlation. Joint distribution, or joint probability mass function, is denoted f sub xy, little x, little y, where the capital X and Y stand for the random variables we are interested in, and the little x and little y stand for the realizations of the random variables. The PMF of X and Y is defined to be the probability that X equals little x and Y equals little y. Often, for two random variables, the PMF can be written in a two-way table, like the one here. In this table, the rows stand for the values, the realizations that one of the random variables can take, say X. So the rows are the values for the X random variable, and the columns are the values for the Y random variable. And in each grid, here we write the PMF value for the pair of values of X and Y. So for the insurance medical expenditure example we just discussed, the probability that X equals 0 and Y equals 100 is 0.8, and probability that X equals 0, no insurance cost is 0, and insurance with insurance cost is 600, that is 0. The probability of that event is 0. And so on and so forth. You can figure out the values for each of these grid. So this two-way table describes the joint distribution of x and y. From the joint distribution, we can also figure out the distribution of each of the random variables. And now we call, in the context of the joint distribution, we call the distribution of each of the random variable the marginal distributions. So there is also the concept of marginal distributions. Marginal distribution is just the distribution of the single variables, but they are called marginal so that we distinguish that from the joint distribution. So the marginal distribution of x can be calculated from the joint distribution by this formula. So just take the joint distribution and sum over y. Similarly, fy can also be calculated this way. We simply sum over x for the joint distribution. For example, in this table, we can write the marginal distribution of x in this column by summing up the numbers on each row. So the probability that x equals 0 can be obtained by summing up these two probabilities. So that is, in this case, 0.8. And similarly for this row, for x equals 500, the probability is 0.19. And for x equals 50,000, the probability is 0.01. Similarly, we can do the same for y. The marginal distribution of y for each value can be obtained by summing up numbers on the column corresponding to that value of y. So the probability that y equals 100 is the sum of these three numbers, which is 0.8. And similarly here is 0.2. For joint distributions, we can also define some traits. And one of the useful traits is covariance. Covariance is a summary of how x and y move with each other. The definition of covariance is here. Covariance of x and y is defined to be an expectation. It's an expectation of the product of the deviation of x from its own mean and deviation of y from its own mean. We can see that if both x and y tend to move in the same direction, that is, if both tend to be above their means at the same time and below their means also at the same time, then these two deviations will tend to have the same sign, meaning covariance will tend to be positive. On the contrary, if x and y tend to deviate from their mean to different directions, to opposite directions, then this product will tend to be negative and covariance will be also negative. So this is why this formula is a good summary of how x and y co-move. Let's consider this example again, the medical expenditure example again, and try to calculate the covariance of x and y in this case. So as you can see, to calculate the covariance, we need to first calculate the mean of each random variable. So the mean of x can be obtained using these marginal distribution numbers. So 0.8 times 0 plus 0.19 times 500 plus 0.01 times 50,000. And that gives us 595. The expected value of y can also be obtained this way by taking the average of these two values with the weights given by the probability mass function. So EY is 0.8 times 100 plus 0.2 times 600, and that gives us 80 plus 120, which is 200. Now that we have EX and EY, we can plug in the expectation formula for this product and get the covariance. Covariance of X and Y, you need to consider all the possible pairs of values for X and Y. In this example, is actually simpler because 3 of the cells have 0 probability, so we will not need to consider these 0 probability cells. We only consider these 3 positive probability cells. So covariance of X and Y equals 0.8 times the value corresponding to this cell, that's 0 and 100, 0 minus EX, 595, times 100 minus 200. That's the first cell. And now consider the second non-zero cell, 0.19 times the value of X corresponding to that cell, that's 500 minus 595 times 600 minus 200. And now the last cell, last non-zero cell is this 0.01. That corresponding to the values of X and Y being 50,000 and 600. 50,000 and 600. And if you do all the calculation on the computer, of course, you can get that this covariance is 238,000. So clearly it is positive, which is intuitive because the medical expenditure in both cases increases with the severity of your illness. So they do move in the same direction. And it is a huge number. The reason for it being so huge is that it is the product of the deviations, and the deviation is huge in one of the cases. The deviation from the mean in this case, in this 0.1 case, is generated by this 50,600 pair of numbers, and that is huge. Well, because covariances can be huge and it's hard to know just by looking at the number what is the strength of dependence between X and Y, because covariance is also affected by the scale of the variables, not only by their dependence. So that is why we often also use another concept, that's correlation. Correlation is in a way scale-free and only captures the dependence between two random variables. What is the definition of correlation? Well, simply, we divide covariance by the standard deviations of the two random variables. And once we divide covariance by the standard deviations of the two random variables, we remove the scale from the covariance statistic and we get the correlation. Correlation of x and y is defined to be this ratio. Now consider the previous example again. We got the covariance. What is the correlation? To get the correlation, we will need to find also the variances of the x and the y. So the variance of x is expectation of x minus e of x squared. X takes these three values. So we're going to take an average of these three values. Point 0.8 using the weights given by the marginal distribution. 0.8 times 0 minus EX. EX, remember we have calculated it to be 595 squared plus 0.19 times 500 minus 595 squared plus 0.01 times 50,000 minus 595 squared. And that turns out to be 2469, 3475. So that's a huge number. And variance of y can be calculated the same way. Y only has two values. So we'll just do 0.8 times 100 minus its mean, which is 200, plus 0.2 times 600 minus 200 squared. And that turns out to be 40,000, which is also quite huge. Now we have all the ingredients to calculate the correlation. Correlation sometimes is also denoted a row subscript x and y. So that's another notation for correlation. Correlation equals the covariance, which we calculated to be 238,000 divided by the square root of sigma x squared times sigma y squared, which turns out to be around 0.24. So this is the approximated equal sign. So the correlation between x and y in this example is about 0.24. So there is quite a bit of positive correlation. Now let's consider some useful facts about covariance. And these facts will be useful for our future study. The first one is that covariance of x itself equals the variance of x. This is a very simple fact and can be seen from the definition of covariance very easily. The covariance of x and x by definition is expected value of x minus e of x times x minus e of x. And within this bracket, that is x minus ex squared. So therefore, that is expectation of x minus e of x squared. And that, remember, is the definition for the variance of x. Now the second claim. The second claim is about the covariance of a linear function of x with y. How does a linear transformation like this affect covariances? Well, it turns out this claim says that the additive constant does not affect covariance, but the multiplicative constant can be factored out of the covariance function. So the covariance of ax plus b and y, by definition, is expected value of ax plus b minus expected value of ax plus b, and that difference times y minus e of y. And to see what this is, we want to first apply the linearity of expectation here for this quantity. That quantity applying the linearity of expectation, we get a times ex plus b. So that equals ax plus b minus a times e of x plus b. Now consider this difference here. The b can be canceled out, and the a can be factored out. So we are left with a times x minus e of x, y minus e of y. Again, use the linearity of expectation again, factor this a out, and we get a times e of x minus e of x times y minus ey. And recall, this is the definition of covariance of x and y. So that's a times covariance of x and y. That proves the second claim. The third claim is about the covariance of the sum of two random variables with y. So now we are involving three random variables. The sum of the sum of x plus x1 plus x2, the sum of x1 and x2 have a covariance with y that equals the sum of the covariances. So as you can see by now, covariance, it's kind of like a product. So you can kind of use the distributive rule of products to deal with covariance. Well, this is not surprising because covariance is defined to be expectation of a product. Now, why is this claim true? We can prove it again, starting with the definition. By definition, this equals expected value of x1 plus x2 minus expected value of x1 plus x2 times y minus e of y. Now, expectation of the sum of the two random variables equals the sum of the expectation, as we have learned before. So that equals x1 plus x2 minus e of x1 minus e of x2. Now let's group the quantities with x1 together and also the quantities with x2 together. And we are left with x1 minus e of x1 plus x2 minus e of x2 times y minus e of y. Now we use the distributive rule for the products. Distributive rule for the products, and distribute the deviation of y from its mean to these two terms. And we get this. Now again, using the property for expectation of the sum of the two terms equals the sum of the expectation. And now realizing that the first expectation is the definition of the covariance between x1 and y, and the second is the covariance between x2 and y. And the next claim is another way to write covariance. Covariance of x and y can be written as expected value of x times y minus ex times e of y. Expectation of the product minus product of the expectation. That is another way to calculate covariance. And this is quite easy to prove as well. We start again with the definition. What we do next is to expand or distribute y minus ey to each of these two terms. So we get x times y minus e of y minus e of x times y minus e of y. Again, using the linearity of expectation of the sum equals sum of the expectation. And we get e of x y minus e of y minus expectation of ex times y minus e of y. Now for the first term, this again we can distribute x to y and to e of y. So that gives us expectation of x times y minus expectation of x times e of y minus. Now for the second term, we first need to realize that expectation of x, that is a constant. It's not random. It takes only one value, one deterministic value. So if it is a constant, it's just like the little a multiplied to the random variable. That means by the linearity of expectation, it can be taken out of the expectation. So we can take the expectation of x out of the expectation. And inside we have e of y minus ey. Now for these terms, e of x and e of x times y stays the way it is. And for this term, again, realizing e of y is non-random, is a constant, just like the little a multiplied to the random variable x, it can be taken out of the expectation. So we get this to be a expectation of x times expectation of y. Right? This is a scalar, so it doesn't really matter I put ey on the left or on the right. It doesn't really matter. And for the rest, notice that e of x can stay where it is. Well, this term is e of y minus expectation of e of y, which is e of y itself because it is a constant already. Notice that it's ey minus ey, and that is 0. Therefore, the final result is e of xy minus e of x times e of y. And that is the claim we started with. Last useful fact for this video clip is the fact about correlation. Well, we claim that the correlation is between -1 and 1. No matter what random variables x and y are, their correlation is always between -1 and 1. And why is this true? Proving this fact, we can use the Kosi-Schwarz inequality. The Kosi-Schwarz inequality states expectation of x times y squared of the expectation of the product is less than or equal to expectation of x squared times expectation of y squared. There is a proof in our textbook for the Kosi-Schwarz inequality. It's not very hard to read, but we're not going to go through that. Kosi-Schwarz inequality is one of the very useful inequalities that we use proving theorems in econometrics. If you're interested, you can have a look at the textbook for the proof. But now we're gonna just use the Kosi-Schwarz inequality to prove that the correlation is between -1 and 1. To do so, we just need to recall that covariance of x and y, which is the numerator for the correlation, covariance equals expected value of a product of two random variables. The two random variables are the deviation of x from its mean and the deviation of y from its mean. We can apply the Kosi-Schwarz inequality on these two random variables, the two deviations, and get the following. That is, the covariance squared is less than or equal to expected value of x minus e of x squared times expected value of y minus e of y squared. Recall that this is the variance of x, and that is the variance of y. Therefore, the absolute value of the covariance is less than or equal to sigma x times sigma y. And remember what the definition of correlation is. Definition of correlation is the covariance of x and y divided by sigma x times sigma y. And that is clearly less than or equal to 1. So the absolute value of the correlation is less than or equal to 1, proving the claim. So because it's bounded between -1 and 1, the correlation -1 and 1 are quite special. If rho is 1, that means x and y are perfectly correlated or perfectly positively correlated. If rho xy equals -1, they are perfectly negatively correlated. If rho equals 0, then they are not correlated. They are uncorrelated. And the value of rho can tell us how x and y are dependent. Can give us a summarizing idea of how x and y are dependent, even though it doesn't give us the whole picture of the dependence between x and y, which is captured by the joint distribution.